Hello everyone, I'm Shibaji Chakraborty from Virginia Tech, and today I'm going to talk about a framework for estimating ionospheric HF absorption in response to solar flare. Before going to start, I would like to thank my collaborators, especially my advisors, Dr. Ruohoniemi and Dr. Baker. They are both from Virginia Tech SuperDARN group, and my other collaborator, Robin Fiori from Natural Resources Canada, from Canada, Ontario, and Kate Zawdie from NRL. So it all starts from the sun, which is the heart of our solar system, and it emits electromagnetic radiation in all spectrums, specifically in X-ray and EUV spectrum. It shoots out the sudden localized intensification of EM radiation, also commonly known as solar flares. And in this particular study, we are going to focus on solar flare impact on the ionosphere. So here is a brief outline of this talk. I'm going to introduce the impact of the solar flare on the traveling radio wave and the ionosphere, and our objective of this study and instrumentation I'm going to use for this study, and then I'm going to talk about the solar flare effect on SuperDARN and riometers, and then I'm going to describe whether we are going to use a SuperDARN as a solar flare monitor, and modeling use of HF absorption using a physics-based framework, and finally I'll summarize all of my finding. So Earth ionosphere, here is the schematic of the Earth ionosphere and the traveling radio waves through the ionosphere. The ionosphere is the ionized part of the upper atmosphere that consists of typically three regions: D region, E region, and F region, color coded by blue, yellow, and red here. And here in the schematic there is a transmitter and receiver, you can see on the earth, and transmitter transmits a radio signal and it propagates through the ionosphere, and it reflects by the by the gradient, electron density gradient in the ionosphere, and it goes back towards the ground and received by the other receiver on the other side of the earth. So you can clearly see that the ionosphere plays an important role on the radio wave propagation and long distance communication link, and it is clearly related to kind of amateur radio or over the horizon communication. Ionosphere is highly variable and it's dependent on solar activity. If something happens on the input from the solar drivers, the response of the ionosphere and its impact on the traveling radio waves changes. So we are specifically primarily focused on the impact of the solar flare in the ionosphere here. So what are the effects of the solar flare? So solar flare produce sudden ionospheric disturbance. Now, what is sudden ionospheric disturbance? A sudden ionospheric disturbance is the enhancement of the plasma density on the dayside D and the lower E region specifically. So here is the schematic that shows how it's happening. Here is the sun, and it shoots out the intense EM radiation during solar flare that enhances the lower part of the D region and E region, and that is commonly known as SIDs, or sudden ionospheric disturbance, and it creates a sudden increase in radio wave absorption in the high frequency ranges around 3 to 300 megahertz, and that's commonly referred as shortwave fade out or radio blackout in common word in general terms, in terms of amateur radio operators. And it also creates sudden frequency change in radio wave frequency, and that by altering the phase path length of the traveling radio wave, which is commonly known as sudden frequency deviation. However, the majority of this talk is related to the shortwave fade out and how we are estimating the HF absorption from using a physics based model and monitor it using SuperDARN radar networks. So here is the motivation of the study. Why do we care about solar flare? It's the first and foremost thing is the space weather. It affects shortwave fade out and sudden frequency deviation, which affects the amateur radio HF communication used in aviation, emergency management system, defense, etc. If you go through these papers, I'll recommend you to go through these two papers that describes why do we care about the space weather and solar flare specifically that creates radio blackouts. And definitely on the other side, we are interested in various kind of space science, like what creates the HF absorption, what creates the frequency anomaly or sudden frequency deviation on the very first place, what drives them. So in that particular context, I would like to take your attention to this particular part, like solar flare induced SIDs. It is the impact on the traveling radio wave, which is the fastest observing space weather phenomena seen on the Earth. So if anything happens on the sun, it takes only around 8 minutes after creating the solar flare on the sun. It hits the Earth and creates the disturbance on the day side of the Earth. So it's the fastest space weather effect seen by our modern technologies. So the instrument we are going to use is first of one of them is SuperDARN. SuperDARN is an acronym of Super Dual Rural Radar Network, and it's an international HF radar collaboration that probes the Earth atmosphere or upper atmosphere, ionosphere. Here is the figure that describes the SuperDARN. There are almost 35 radars operating in both the hemisphere, northern and southern hemisphere, and the the propagation of the HF rays in the coming from the SuperDARN is dependent on the refraction due to ionospheric electron density gradient. Here is there is specifically two different types of backscatter data product what we are rely on from the SuperDARN. One is known as ionospheric scatter, given by this ray 1, which is, you can see the radar the ray is refracted from the F region irregularities or electron density irregularities. So they are known as ionospheric scatter, and during the daytime the ray bends back completely towards the ground, and it hits the ground on the other side of the Earth, and then it coming back through the same path. And that type of rays or scatters are known as ground scatter. In this particular plot, if you look carefully, the radar scan, it shows two different types of band. One is on the color gray, and another is color coded by the on the right hand side of the color bar. And this shows a particular radar scan, and this particular gray patch is the ground scatter, while this colored patch is the ionospheric scatter. So typically the ground scatter velocity is really low, and it typically lies between plus minus 10 meter per second. So ground scatter replicates exactly a ground-to-ground communication link, just like if you think about amateur radio or long-distance communication links. And the ground. So, and for this particular study, we are only going to use the ionospheric we are going to use the ground scatter data for ionospheric response to solar flares. So another instrument we are going to use is known as riometer. Riometer is relative ionospheric opacity meter. It's a passive radio receiver, unlike the SuperDARN, which is an active one. And this provides the information about the HF absorption in dBs of the ionosphere by variation in cosmic radio noise. So its typical operating frequency is around 30 megahertz. And here is an example of solar flare impact on the riometer, where you can see like the background the riometer observation is around 0 dB, and it suddenly jumps up to 2.5 dB, and it comes back to background again. So this is the riometer station name is Ottawa here. So moving into the data analysis part. So first we are going to see how solar flare affects the SuperDARN radar. This is an event study, which is the 5th May 2015, and these are the field of view plot from Blackstone radar, showing the Doppler velocity in a 4-minute apart scans. So you can see this gray band is the ground scatter, and as you can see, there is a sudden jump in background velocity of the ground scatter, and then it's a complete wipeout. There is no data present in here, and then it gradually backs to pre-shortwave fade out condition. And this particular phase, when there is no data or less number of data than the background condition, it's typically referred as absorption effect or shortwave fade out. That is, I introduced a couple of slides back, or radio blackout phase. And This part where this is relatively newer achievement in our field in which is sudden frequency deviation or Doppler flash. We typically call it as a Doppler flash. So it's a huge amount of velocity rush or velocity increase in the back Doppler on the ground scatter, which reaches around 100 meter per second. So that is a signal of sudden frequency deviation. So here is the same data in RTI plot, which is a range time plot, and you can clearly see the top panel shows the power and the bottom panel shows the velocity, color coded by color bar on the right. And you can clearly see this is a gray band of ground scatter, which is located here. It's identified as ground scatter, and suddenly there is a sudden intensification of ground scatter velocity around 100 meter per second, which is the Doppler flash, and then there is a complete whiteout in the data, and looks like the machine stopped or radar stopped working, but it isn't. It's the absorption effect or shortwave fade out effect. So the timing analysis, we did the timing analysis for this particular event for Blackstone radar. So the top panel shows the Gauss X-ray, second panel shows the average power, third panel shows number of ground scatter echoes detected by Blackstone radar, and the last panel shows the Doppler velocity, average Doppler velocity. So the jump over here on the very first panel is the signature of the solar flare detected by the Gauss X-ray sensors, and on the similarly on the second panel, the bite out in the average background power here, it's the absorption effect. You can clearly see before the complete bite out there is a decrease in the amount of background average power. And similarly on the, if you think about the third panel, if you see the third panel, the ground number of ground scatter, it completely wiped out around this time, which is 22 or 10, but before 22 or 12. But before that, there is a phase when there is a significant drop in the background number of ground scatter echoes. And finally here on the last panel, the sudden jump in the velocity, it's typically we called it as the Doppler flash. So here is a detailed analysis of what we got in timing analysis. The very first line over here, if you think about it, on the third panel where we did the ground scatter echoes, is the onset of the HF absorption. Before this time, there was everything in quiet, and after this time, there is suddenly a change we can see in the number of ground scatter echoes. This one is the start of this black line is the start of radio blackout, which is the start of HF absorption phase. This blue line is the recovery or the start of the recovery. After this point, you can see there is a gradual increase in the background ground scatter echo. So you can think of like it is the ionosphere is kind of recovering. And finally, this is the point which is like almost the ground scatter has been recovered, this green line detected by that. So the different phases identified, unlike there are three different phases identified by these four vertical lines. So from between red to black, we call it onset or precursor of the absorption. From between black to blue, we called it radio blackout, and from this blue to green, we call it a gradual semi logarithmic recovery to restore back to pre-flare condition. We developed an algorithm that detect these phases in the SuperDARN ground scatter data. So we used it for multiple radar at different latitudes. We find like the backscatter signal of the radar located near the subsolar points are more affected more severely than the radars which are located at the higher solar zenith angle or larger solar zenith angle. And this is kind of expected, and you can clearly see like the radar located away from the subsolar point are impacted less severely than radars are located uh, near to the subsolar point. Similarly, we also found the backscatter signal of the radar operating at relatively lower frequencies are really affected more severely than the radar operating at higher frequencies. So if you compare the Blackstone, which were operating nearly 15 megahertz versus the Capus casing radar, which is operating at 10.4 megahertz, although they have almost similar the solar zenith angle, and the Blackstone radar is impacted less severely than the Capus casing radar. So we have taken care of all of this timing analysis, and we find out we can do we can monitor the solar flare effects on the on using the SuperDARN radar. So here is a typical image of north hemisphere with all the radar laid over. Most of the radars are coming from the northern American landmass, and we use this map to distributed radar to find out whether when the solar flare happens. And the green shows the pre-shortwave fade out or normal condition, red shows the onset, black shows the blackout, blue shows the recovery, and yellow shows the data unavailable from the radar. And the bottom of this particular image shows the time scale. So we are going to run a particular event from 2017 solar flare, number of solar flare. One of the solar flare was X 8.3 class, and we are going to play that. So it's running, and you can clearly see the radar progress, the event progress from the northern hemisphere to the southern, and from the east coast to west coast. And yeah, it ran only once. Yeah, it stopped. So the response is I only ran it for one up to the blackout phase. I didn't run the full movie. The full movie is it's loaded in the loaded in somewhere in my poster. So next part is the flare impact on the riometer and the modeling of that HF absorption. So as I already showed you, like this is the top panel is the GOES X-ray data, and the bottom panel is the riometer from the riometer observation from the Ottawa station. And here this enhancement in background absorption, HF absorption, is shown in these black dots. So we want to model this enhancement in the radio blackout, and HF absorption model is presented over here. So this particular model takes an input of f10.7 go soft X-rays and hard X-rays, and outputs the HF absorption height profile in dB per kilometer. So what we did is like we modified the solar irradiance UVAC model. So we called it UVAC plus. The background of the solar irradiance model cover 37 wavelength bands starting from 0.05 to 175 nanometer, using f10.7 as an input. And if you go check the Solomon et al. 2005 paper for that. And we modified the GOES the UVAC model by using the GOES satellite data for last two bins. We modified the last two bins, or the shortest wavelength of the UVAC bins, via GOES datasets, so that it can incorporate the flare time condition. Then we use an ionospheric chemistry model, which constituents four different types of ionospheric constituents, and it try to estimate the electron density, which is given here in Ne. And then after estimating the electron density, we consider a combination of two dispersion relation and four collision frequency profile here, and we compare them with and try to estimate the absorption from there. And we compare the results with the DRAP, D region absorption prediction from NOAA, with the riometer data. And here are the combination of dispersion relation and collision frequency over here. You can clearly see, like, the table shows the UVAC plus as the irradiance model, and then we use dispersion relation Appleton-Hartree and Shane-Weiler, and Appleton-Hartree with all four of these dispersion relation, the collision frequency, whereas Shane-Weiler with only monoenergetic collision frequency. So here is the model, data model comparison. The figure on the left shows a comparison of HF absorption using different dispersion relation and collision frequency combination, and Ottawa riometer data in response to solar flare of 11th March. And these all the red dashed, so the dot in gray are the data from the riometer. The dashed line over here, is the DRAP. And these solid lines are different combination of Appleton, different combination of dispersion relation and collision frequency. For example, this blue line is the Appleton-Hartree collision frequency, Appleton-Hartree dispersion relation with average collision frequency, and the average collision frequency is estimated using Maxwell-Boltzmann integration. Whereas if you consider this green line over here, which is the Appleton-Hartree with the average collision frequency, but the average collision frequency is estimated using a Chapman-Cowling integral. And the red line is Appleton-Hartree with Shank-Nagy average collision frequency. And the black line is Schoenweiler dispersion relation with monoenergetic collision frequency. So from this data model comparison, we find like the black line, which is the Schoenweiler dispersion relation with monoenergetic collision frequency, the best reproduces the riometer observation. However, this Appleton-Hartree dispersion relation with the Shank-Nagy and Chapman average collision frequency, which is Chapman-Cowling integral, also reproduces significantly good data agreement with the riometer observations. So here is the summary of this study. We find like the daytime ground scatter replicates the ground-to-ground communication link, and that makes it really susceptible to solar flare, and we can use it as a tool to monitor the ground scatter, solar flare in the ionosphere. We can see the progression of different phase timings along the latitude and longitude, and solar zenith angle. We find like timings are also constrained by the transmitted frequency of the radar. Radar with the high operating frequency are affected much lower, and radars operating low frequencies are affected more severely. And finally, we showed that a proof of study concept that shows a subnet of SuperDARN HF radars can be used to monitor solar flare driven HF absorption across the North American sectors. And we are planning to build a real-time monitor such that we can monitor the solar flare, or any deviation in absorption in the HF absorption can be monitored using SuperDARN network. Finally, from the modeling event study, we showed that the Schoenweiler dispersion relation with the monoenergetic collision frequency at best reproduces riometer observation. However, there is a clearly that begs a follow-up study to a more statistical way to prove this particular sentence, or check whether which combination of dispersion relation are best fit to produce this solar flare driven HF absorption. Thank you. If you have any question, please ask me or email me in this particular email address, shibaji7@vt.edu. And I would like to thank NASA and NSF for their grant, which is supported to support this particular study. Thank you.